Welcome! Today, we'll be exploring an interesting problem from LeetCode titled Group the People given the group size they belong to. This problem challenges us to effectively group individuals based on their specified group sizes. We'll break it down step by step, explore different approaches, and analyze their complexities. Let's dive in. In this problem, we are tasked with grouping people based on their specified group sizes. Each person is represented by an index in the array group sizes, and the value at group sizes, I, tells us the size of the group that person I belongs to. For example, if group sizes, I, is 3, that means person I belongs to a group of exactly 3 people. Our goal is to create and return a list of lists, where each sublist contains the indices of people in a single group, and each group has the exact size specified for its members. It's important to note that the order of the groups in the output and the order of members within each group do not matter, as long as the constraints are met. This gives us some flexibility in how we organize the output. To summarize, we need to ensure each person is included in exactly one group, and every group has the correct number of members. Now, let's look at an example to understand this problem better. Suppose the input is group sizes equals 3333313. Here, person 5 has a group size of 1, so they form their own group, represented as 5. Next, persons 0, 1, and 2 all belong to a group of size 3, so they form another group, represented as 0, 1, 2. Similarly, persons 3, 4, and 6 also belong to a group of size 3, forming the group 3, 4, 6. The output in this case is 5, 0, 1, 2, 3, 4, 6. Notice that while the groups are ordered this way in the output, the order of groups or members within each group can vary as long as the constraints are satisfied. This flexibility allows multiple valid solutions. Let's consider another example. If the input is group sizes equals 2, 1, 3, 3, 3, 2, person 1 has a group size of 1, so they form their own group, 1. Persons 0 and 5 both belong to a group of size 2, so they form the group 0, 5. Finally, persons 2, 3, and 4 all belong to a group of size 3, forming the group 2, 3, 4. Therefore, the output in this case is 1, 0, 5, 2, 3, 4. Once again, the specific order of the groups or the members within them is not important, as long as the constraints are met. For instance, we could list 2, 3, 4 before 0, 5, and it would still be a valid solution. Here's another example to illustrate a simpler case. If the input is group sizes equals 1, 1, 1, 1, each person belongs to a group of size 1. This means that every person forms their own group. The output in this case is 0, 1, 2, 3. This scenario is straightforward because there's no overlap in group sizes, and each person is isolated in their own group. It's also worth noting that this is just one of the edge cases we might encounter, and we'll discuss more edge cases shortly. Now, let's explore a few important edge cases. First, if the input consists of just one element, such as group sizes equals 1, the output will simply be 0, since there is only one person who forms their own group. Another edge case is when all group sizes are 1, as we saw earlier. In this case, each person forms their own group individually. On the other hand, if all group sizes are equal to the length of the array, such as group sizes equals 4, 4, 4, 4, everyone belongs to one large group, resulting in the output 0, 1, 2, 3. Finally, for mixed group sizes, we need to carefully match groups iteratively, ensuring that every person is placed into a group of the correct size. This iterative process is key to solving the problem while respecting all constraints. When tackling the problem, one approach to consider is the brute force method. The intuition behind this is straightforward. As we iterate through the input list, we manually form groups by matching people to their required group sizes. For each person, we try to add them to a partially filled group that matches their size. If no such group exists, we create a new one. Once a group reaches its required size, we finalize it and move on to the next. This method is simple to implement but comes with significant drawbacks. The repeated searches for partially filled groups make it inefficient, resulting in a time complexity of O(n)². While the space usage is manageable at O(n), the brute force approach struggles to scale effectively for larger inputs, making it less suitable for competitive programming scenarios. To address the inefficiencies of the brute force method, we can turn to an optimized approach using a hash map. The key insight here is that each person's required group size can act as a unique key, allowing us to efficiently manage groups. By mapping each group size to a list of people who belong to that group, we eliminate the need for repetitive searches. As we iterate through the input, we add each person to the corresponding group in the hash map. When a group reaches its desired size, we finalize it, append it to the result list, and reset the list for that group size. This approach is highly efficient, with a time complexity of O(n), since each person is processed exactly once. The space complexity remains O(n), used for both the hash map and the result list. Here's a snippet to illustrate the first part of the implementation. We initialize a hash map using collections.defaultDict and iterate through the input, appending each person to their respective group. As the process continues, we check if the current group has reached its required size. If it has, we finalize the group by appending it to the result list and resetting the group in the hash map to an empty list. This ensures that the hash map remains lightweight and ready to handle new groups efficiently. Once all people have been processed, the result list contains all the finalized groups, which we then return. This approach balances clarity and efficiency, making it an excellent choice for large inputs. While slightly more memory intensive due to the hash map, the trade-off is well worth it for the dramatic improvement in time complexity. Additionally, this method is straightforward to implement and avoids the pitfalls of redundant computations. Moving forward, we'll briefly explore an alternative sorting-based approach for further comparison. The sorting-based approach takes a different route by first pairing each person with their group size and then sorting the array based on the group sizes. This allows us to process people in order of their group requirements. As we traverse the sorted list, we collect people into groups, finalizing each group as soon as it reaches its desired size. While this method is systematic and effective for moderate input sizes, it introduces a notable overhead from the sorting step, which has a time complexity of O(n) log n. Additionally, the space complexity remains O(n) for storing groups. Compared to the hash map approach, sorting adds unnecessary computational effort, making it less optimal for very large inputs. Thus, while viable, it's generally not the preferred solution when efficiency is crucial. The breakthrough in our chosen strategy came from recognizing that the group size itself could serve as a key to efficiently manage groupings. This insight eliminated the need for repetitive searches in the brute force method and avoided the overhead of sorting in the alternative approach. By directly leveraging a hash map, we achieved a solution that is both efficient and scalable, with linear time complexity and manageable space usage. This balance of clarity and performance makes the hash map approach the optimal choice for solving this problem, especially when dealing with large datasets. It's a concise and intuitive strategy that not only simplifies implementation but also ensures robust performance under constraints. In this problem, we are tasked with grouping people based on the sizes specified in the group sizes array. Each person, represented by their index in the array, belongs to a group of a specific size indicated by the value at that index. Our goal is to partition all individuals such that every group contains exactly the required number of people, and each person belongs to one and only one group. To tackle this, we start by considering a brute force approach. The intuition behind this approach is to iterate through the input array and form groups incrementally. As we process each person, we add them to a temporary collection until the group reaches its required size. Once the group is complete, we finalize and store it. To implement this, we initialize two key data structures, a list called groups to store finalized groups, and a dictionary called in_progress to keep track of groups that are still being formed. The dictionary helps us organize individuals based on their group size and ensures we can efficiently build and finalize groups as we process the input. The next step in the brute force approach is to iterate through each person in the group sizes array. For every person I, we first retrieve their required group size from the array. Using this size, we check if there is an ongoing group being formed in the in_progress dictionary. If no such group exists, we create a new key value pair in the dictionary with an empty list for that size. Then, we add the current person to this list. If the group for this size reaches the required number of people, we finalize it by appending the list to the group's collection and removing the corresponding entry from in_progress. This ensures that the dictionary always reflects the groups currently being formed, without unnecessary clutter. Once we've processed all individuals in the array, all groups will have been finalized, and the result will be stored in the groups list. Finally, we return groups as the output. This step-by-step process ensures that every person is placed in exactly one group, and all groups meet the specified size requirements. Using a dictionary like in_progress is key to this approach because it allows us to efficiently track groups being formed by their required sizes. Without it, we would need to search through a list to find an appropriate group, which would significantly increase processing time. This method ensures that each person is processed only once, resulting in an overall time complexity of O(n), where n is the number of people in the group sizes array. Additionally, this approach is robust enough to handle edge cases. For instance, when all group sizes are 1, each person forms their own group. Similarly, if all group sizes are equal to the array length, there is only one large group containing everyone. It also handles mixed sizes where group sizes vary significantly, ensuring that no matter the combination of sizes, the solution remains efficient and accurate. To implement this solution, two main data structures are vital. First, the list groups is used to store all finalized groups. For example, if the input is group sizes equals 3, 3, 3, 1, 1, the groups list could look like 0, 1, 2, 3, 4, where each sublist represents a valid group. Second, we use the dictionary in_progress to manage partially formed groups. This dictionary has keys representing the group sizes and values as lists of people currently being added to that group. For instance, while processing the third person in the same example, in_progress might look like 3, 0, 1, 1. To optimize further, we minimize dictionary operations by removing keys as soon as a group is finalized. Additionally, finalized groups are directly appended to the groups list to reduce memory overhead and improve performance. Now, let's analyze the algorithm's complexity. The time complexity is O(n), since we process each person exactly once to either add them to an ongoing group or finalize their group. The space complexity is also O(n), as both groups and in_progress require storage proportional to the number of people in the input. To better understand, consider the input group sizes equals 3, 3, 3, 1, 1. Initially, we set up groups as an empty list and in_progress as an empty dictionary. For person 0 with group size 3, we add them to in_progress 3, making it 3, 0. Next, person 1 joins the group, updating it to 3, 0, 1. When person 2 is added, the group reaches size 3, so we finalize it by appending 0, 1, 2 to groups and clearing in_progress. This process continues for the remaining individuals, creating groups 3 and 4 for the other two people, resulting in the final output 0, 1, 2, 3, 4. Finally, once all individuals are processed, we ensure that every group is finalized and stored in the groups list. For example, after processing person 3 with group size 1, we add them to in_progress 1, resulting in 1, 3. Since this group reaches the required size immediately, we finalize it by appending 3 to groups and clearing in_progress. Similarly, when person 4 is processed, they form another group of size 1, which is finalized as 4. At this point, all groups are complete, and the final output is 0, 1, 2, 3, 4. This approach ensures correctness and efficiency, handling all edge cases and leveraging the simplicity of dictionary-based lookups and operations to achieve an optimal solution. This solution tackles the problem by using a dictionary to group people based on their group sizes. The dictionary, groups, maps each group size to a list that temporarily holds the people belonging to that group size. The result list stores the final groups once they are complete. The code loops over each person, enumerate group sizes, where person is the index and size is the group size of that person. If the group size is not already in the dictionary, it initializes an empty list for that size. Each person is then appended to the corresponding list in groups. Whenever the list for a specific group size reaches the required size, i.e., len groups size equals size, it means the group is complete. At this point, the complete group is added to the result list, and the list for that group size in groups is reset to an empty list to continue collecting new members for subsequent groups of the same size. This approach ensures that each person is processed once, and groups are dynamically created and finalized as needed. The overall time complexity of the solution is O(n), where n is the length of the input array group sizes, since each person is added to a group exactly once. The space complexity is also O, n, as we use additional space to store the intermediate groups in final output. Here, we start by importing the necessary Java utilities, like hashmap and ArrayList, which will help us manage and group the data. Inside the solution class, we define the method groupThePeople, which takes an array of integers called groupSizes. This array represents the group size each person belongs to, where the index in the array corresponds to the person. First, we create a hash map called groups to map each group size to a list of people. This will help us organize people by their group size dynamically. Additionally, we initialize a list of lists called result, which will store the final groupings of people. Next, we iterate over the group sizes array using a for loop, where person represents the index, and we retrieve the corresponding group size using group sizes person. If this group size is not already in the map, we use putifAbsent to initialize an empty list. Then, we add the current person to the appropriate group in the map. If the size of the group reaches the required limit, we add this group to the result list and clear the group in the map to allow for new groupings of the same size. Finally, the result list, which now contains all the correctly grouped people, is returned. This ensures that each group in the result matches the size specified in the input array. By utilizing a hash map and dynamically managing the groups, this approach efficiently organizes the data into the required structure while adhering to the constraints of the problem. In this example, we start with the input group sizes equals 333313. The first step is to initialize two structures, an empty dictionary called groups to temporarily store people based on their group sizes, and an empty list called result to store the final groups. As we iterate over the list, the first person, person 0, has a group size of 3. Since group size 3 is not yet in the groups dictionary, we initialize it as an empty list. Then, we add person 0 to this list, so groups becomes 3, 0. Moving to the second person, person 1 also has a group size of 3. We add them to the existing list under group size 3, making groups 3, 0, 1. For the third person, person 2, we repeat this process, adding them to group size 3, resulting in groups 3, 0, 1, 2. Since this list now has 3 people, which matches the group size, we move it to the result list, updating result to 0, 1, 2. After this, we reset the group size 3 in the dictionary, making groups 3. Continuing, person 3 also has a group size of 3. We add them to the list for group size 3, so groups becomes 3, 3. Similarly, person 4, who also belongs to group size 3, is added to the list, updating groups to 3, 3, 4. Now we encounter person 5, who has a group size of 1. Since group size 1 is not in the dictionary, we initialize it as an empty list and then add person 5 to it, updating groups to 3, 3, 4, 1, 5. Since this group size has reached its capacity of 1, we move it to the result list, making result 0, 1, 2, 5. We then reset group size 1 in the dictionary, leaving groups as 3, 3, 4, 1. Finally, for person 6 with a group size of 3, we add them to the existing list under group size 3, updating groups to 3, 3, 4, 6. This group is now full, so we move it to the result list, giving us result equals 0, 1, 2, 5, 3, 4, 6. We reset group size 3 in the dictionary, leaving groups as 3, 1. Our final output for this example is 0, 1, 2, 5, 3, 4, 6. Here, we start with a new input, group sizes equals 2, 1, 3, 3, 3, 2. As before, we initialize groups as an empty dictionary and result as an empty list. The first person, person 0, has a group size of 2. Since this group size is not yet in the dictionary, we initialize it as an empty list and add person 0 to it, making groups 2, 0. Next, for person 1, who has a group size of 1, we initialize group size 1 in the dictionary and add person 1 to it, updating groups to 2, 0, 1, 1. This group is now full, so we move it to the result list, resulting in result equals 1. We then reset group size 1 in the dictionary, leaving groups as 2, 0, 1. For person 2, with a group size of 3, we initialize group size 3 in the dictionary and add them to it, so groups becomes 2, 0, 1, 3, 2. Next, person 3 also has a group size of 3. We add them to the existing list for this group, updating groups to 2, 0, 1, 3, 2, 3. Similarly, person 4 with the same group size is added to the list, resulting in groups 2, 0, 1, 3, 2, 3, 4. This group is now full, so we move it to the result list, updating result to 1, 2, 3, 4. We reset group size 3 in the dictionary, leaving groups as 2, 0, 1, 3. Finally, person 5 has a group size of 2. We add them to the list for group size 2, making groups 2, 0, 5, 1, 3. Since this group is now full, we move it to the result list, resulting in result equals 1, 2, 3, 4, 0, 5. We then reset group size 2 in the dictionary, leaving groups as 2, 1, 3. The final output for this example is 1, 2, 3, 4, 0, 5. In this example, we have group sizes equals 1, 1, 1, 1. As always, we start by initializing groups as an empty dictionary and result as an empty list. The first person, person 0, has a group size of 1. Since this group size is not yet in the dictionary, we initialize it and add person 0 to it, making groups 1, 0. This group is now full, so we move it to the result list, updating result to 0. We reset group size 1 in the dictionary, leaving groups as 1. Next, person 1 also has a group size of 1. We add them to the list for this group, updating groups to 1, 1. Since this group is now full, we move it to the result list, resulting in result equals 0, 1. We reset group size 1 again, leaving groups as 1. For person 2, who also has a group size of 1, we add them to the list under group size 1, updating groups to 1, 2. This group is now full, so we move it to the result list, making result equals 0, 1, 2. We reset group size 1, leaving groups as 1. Finally, person 3 has a group size of 1. We add them to the list, updating groups to 1, 3. Once again, this group is full, so we move it to the result list, resulting in result equals 0, 1, 2, 3. After resetting group size 1, groups becomes 1. The final output for this example is 0, 1, 2, 3. To analyze the time complexity of this solution, we start by considering the main operations in the algorithm. First, the algorithm iterates through the group sizes list exactly once. If we denote the length of group sizes as n, this iteration contributes O(n) to the time complexity because it is performed in a single for loop. Next, during each iteration, the algorithm performs a dictionary lookup to check if the current group size exists in the group's dictionary. Since Python dictionaries are implemented as hash tables, this lookup is an average O(1) operation. Additionally, the algorithm appends the current person to the corresponding group list, which is also an O(1) operation. Because these operations are repeated for each element in group sizes, their combined contribution remains O(n). Finally, whenever a group reaches the required size, it is appended to the result list, which is a constant time operation, O(1). Over the entire process, this appending step occurs exactly once per group, meaning its total contribution is proportional to the number of elements in group sizes, or O(n). Overall, all these steps combine to give the algorithm a total time complexity of O(n). Thus, when we sum up all the contributions, the overall time complexity of the algorithm is O(n). Let's now examine the space complexity. The space usage is determined by the storage requirements of the group's dictionary and the result list. The group's dictionary is used to store temporary lists of people for each group size. In the worst-case scenario, where every person has a unique group size, the dictionary would store n keys, each pointing to a list with a single person. This results in a space usage of O(n) for groups. The result list contains the final groups. Since each person from the input list appears in exactly one group, the total space required for result is also O(n). Apart from these, the algorithm uses a few additional variables like person, size, and group sizes, which require constant space, or O(1). Combining these factors, the overall space complexity of the algorithm is O(n). The efficiency of this algorithm can be better understood by comparing it to a brute force approach. A naive solution might repeatedly scan the group sizes list to form groups, leading to a time complexity of O(n) squared, in the worst-case scenario, such as when all group sizes are the same. In contrast, this algorithm achieves O(n) time complexity by making a single pass through the input and using dictionary lookups, which are O(1) operations. As for space complexity, the algorithm's O(n) usage is optimal because we must store all n people in groups, and it is not possible to reduce this requirement further. When analyzing different cases, the best case scenario occurs when all group sizes are 1. Here, the algorithm still iterates through the input once, making the time and space complexity O(n). In the average case, where group sizes are distributed randomly, the complexity remains O(n) due to the single pass approach and dictionary usage. Finally, in the worst case, such as when all group sizes are unique or there is one very large group, the algorithm still performs efficiently with O(1) operations per element, leading to O(n) time and space complexity. To mathematically confirm the big O complexity, we note that the algorithm processes each of the n elements in the input exactly once. During this processing, it performs a constant number of O(1) operations for each element, such as dictionary lookups and appending to lists. This means the total time complexity is O(n). For space complexity, the group's dictionary and result list are the main contributors. The dictionary can hold up to n keys in the worst case, each pointing to a temporary list, and the result list stores all n people. This proportional relationship to the input size n confirms the space complexity is O(n). These findings demonstrate that the algorithm is both time and space efficient, making it well suited for this problem. When solving this problem, there are some common mistakes that can trip you up if you're not careful. First, many people overlook the importance of grouping efficiently. For example, trying to form groups without utilizing a dictionary or hash map to organize people by their required sizes often leads to redundant iterations and an inefficient solution. This can unnecessarily increase the time complexity of your code. Another mistake is misunderstanding the problem constraints. Some might assume that the group sizes values are entirely arbitrary or unbounded, but the constraints typically provide useful limits. For instance, group sizes are often between 1 and the length of the input array. Ignoring these constraints can result in solutions that are unnecessarily complex or suboptimal. Lastly, it's easy to overlook edge cases. For example, if all group sizes are identical, or if the input consists of the smallest possible groups, like all ones, your solution needs to correctly handle these scenarios. Making assumptions about input diversity could lead to incorrect outputs in these cases, so validating edge cases is essential. Another common pitfall in this problem is modifying the input data directly while iterating. For instance, changing the group sizes array as you loop through it can cause logical errors or result in skipped elements, especially if you're relying on the original indices. It's better to work with a copy of the data or use additional structures to avoid these issues. Similarly, overcomplicating your algorithm can be a major drawback. Some solutions use nested loops unnecessarily or resort to brute force approaches that don't take advantage of the problem constraints. While brute force may seem straightforward, it becomes problematic when the input size grows, as this can easily push the time complexity to O(n squared, which is not acceptable for larger inputs like n equals 10⁻⁴. Instead, you should aim for a more streamlined approach that avoids these inefficiencies. To approach this problem effectively, it's important to understand the key insights. One of the most important ideas is recognizing that the problem can be solved efficiently using a hash map. By grouping people based on their required group sizes, you can iteratively form the groups without redundant processing. This aligns with a common pattern in algorithmic problems, grouping elements in a list based on some classification criterion. Mastering the use of hash maps for grouping is a valuable skill for tackling similar problems. In terms of performance, aim for a solution with O(n) time complexity, as sorting is unnecessary here and would increase the complexity to O(n log n). In interviews, it's also important to explain trade-offs. While brute force methods might be easier to implement, they're far less efficient than a hash map-based approach, which is both optimal and elegant when implemented correctly. Finally, if you want to practice similar problems, you might explore LeetCode 49, which deals with grouping anagrams using hash maps, or LeetCode 763, where the goal is to partition labels optimally. Each of these problems reinforces the concept of grouping and processing efficiently. Now let's discuss some alternative approaches to solving this problem. The brute force approach involves manually iterating through the group sizes array and forming groups one by one. While this method is simple to implement, it's highly inefficient, with a worst-case time complexity of n squared. For larger inputs, this is not feasible. A much better option is the hash map grouping approach. Here, you use a hash map to group indices by their required sizes, and then form the groups directly. This method is both efficient and elegant, achieving an optimal time complexity of n. However, it does require additional memory to store the hash map. Another possible approach is sorting the group sizes array and processing the groups sequentially. While this might seem logical, sorting increases the time complexity to n log n, which is unnecessary for this problem. In most cases, the hash map solution is the best choice, as it balances speed and clarity. Great job! We've successfully broken down the problem and walked through a clean and efficient solution. Remember, mastering hash maps is essential for tackling grouping and categorization problems like this. Thank you for watching, and make sure to stay connected for more engaging problem-solving sessions. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!